The second part of Chapter 5, Section 6 is going to deal with the area between two curves. And we're going to look at this from two perspectives. In the first case, we're going to look at if we have an upper and a lower curve. To find the area in between those two curves, you're going to integrate with respect to x, and you just take the upper minus the lower curve. Sometimes this is going to cause you to have to maybe separate your interval, break it up a little bit, and we'll do an example with that in a minute. Other times, you might be asked to find a region between two curves where the curves are not one on top of the other, but to the left and right of one another. And in that case, you're going to integrate, not differentiate, integrate with respect to y, and you'll take the rightmost curve minus the leftmost curve in that case. Okay, so it's either going to be top minus bottom, and you'll integrate with respect to x, or right minus left, integrate with respect to y. So we're going to do some examples of these. Notice here it says find the total areas of the shaded regions. This first example actually goes back to the first page of the notes. This function is symmetric with respect to the origin. It's an odd function. That means if I were to integrate from -2 to 2, it would be a wash because the area that's above the x-axis is equal to the area that is below it, except they'd be opposites of each other. So when you add them together, you're going to get a 0. But it asks me for the total area. When you see total area, think absolute value of the areas. So what I want to do is find the area down here, which would be a negative value, but we're going to look at the absolute value of it, and then we'll find the area over here. Now, because this is symmetric with respect to the origin, the only difference between this area and this area is this one is negative, but they have the same absolute value. So to save a little bit of time, you only need to find one of these two and then just double it to get that total area, because again, I'm looking at absolute value area. So what I'm going to do is I'm going to find the area of the region between the curve and the x-axis from 0 to 2, and again, we're just going to double that value. So it's going to be 2 times the integral from 0 to 2 of x times the square root of 4 minus x squared dx. We're going to use u substitution here, and this is actually the last example in this section where we're going to do u substitution. The other is going to be a little more straightforward. And in this case, I'm going to let u equal what's inside that radical. So u equals 4 minus x squared. du is then going to be -2x dx. Now, I'm part way to where I need to be for this du. I can bring the 2 to the other side of the integral, but I'm missing that negative. So what I can do is just put a negative in front and make that a -2x on the inside. So you'll see I now have my -2x, and then there's the dx to create that du. So I can go ahead now and do my u substitution. Can't forget the negative in front. And I'm going to change my upper and lower bounds here. If x is 0, 4 minus 0 squared is going to be 4 minus 0, which is still 4. If x is 2, 2 squared is 4, so 4 minus 4 is 0. And then I have the square root of u du. Now what I can do, I can get rid of this negative here if I flip my upper and lower bounds, and I'm going to go ahead and do that. So it's now going to go from 0 to 4 instead of the other way around. And I'm going to write the square root of u as u to the 1/2 power. When I integrate, I'm going to have u to the 3/2 over 3/2, and I can write that instead as 2/3 u to the 3/2. And again, we're going to evaluate from 0 to 4. I'm going to pull the 2/3 in front. So what I'm looking at, it's a funny looking parenthesis, it's going to be 4 to the 3/2 minus 0 to the 3/2. Well, 0 to the 3/2 is still going to be 0, so I don't need to worry about that, but I'm going to look at 4 to the 3/2 power. The square root of 4 is 2, and then 2 cubed is 8, so I end up with 2/3 times 8, or 16/3. And that would be my total area. That would be if I took the absolute value of the region down here plus the area of the region up here, I would get 16/3. What that would tell me is the region above the x-axis is equal to 8/3. The region below would be the negative 8/3, but again, taking the absolute value of both and adding, our total area is 16/3. The second example here on this page, we're going to integrate with respect to y on this one. So here I don't have one curve above another, but they're to the left and right of one another. So when we integrate with respect to y, it's going to be the right curve, which is defined as x equals 12y squared minus 12y cubed, minus the left curve, x is 2y squared minus 2y. Since this is with respect to y, I'm going to look at my y values for the lower and upper bounds. It's going to go from 0 to 1. And again, it's going to be the rightmost curve minus the left curve. And again, we're differentiating with respect to y. So what does that give me? If I drop the negative here, I end up with 12y, or not drop it, but carry it through that second parenthesis. I get a negative 2y squared plus 2y. And then combining like terms, I end up with negative 12y to the third plus 10y squared plus 2y. So let's go ahead and integrate this with respect to y. For the first term, I'm going to end up with negative 12y to the fourth over 4. In the middle, it's 10y to the third over 3. And the last one is 2y squared over 2. I'm looking at that from 0 to 1. I will clean this up. Negative 12 over 4 is negative 3, and then the 2's will cancel on the right. So this is the same thing as negative 3y to the fourth plus 10y cubed over 3 plus y squared. Starting with the 1, I'm going to have negative 3 times 1 to the fourth, that's still negative 3. 10/3 times 1 to the third, so it's 10/3, plus 1 squared, which is 1. When we move to the 0, plugging in a 0 for y gives me a 0 across the board, so it's just going to be minus 0. So over here, I need to have common denominator to add, so we get negative 9/3 plus 10/3 plus 3/3, and adding together, we're going to get an area of 4/3.